Hello, everyone. Welcome to our lecture number 3, Introduction to Atmosphere. In this lecture, we are going to learn basic facts and interesting phenomena in our atmosphere, our very first sphere in Earth's system. You're going to read chapter number 2, Portrait of the Atmosphere. Okay. In our live meeting, I'm going to share this video with you. Have you ever considered jump from our atmosphere back to the ground? Well, this guy Felix, he did it in 2015, I guess, from stratosphere. So stratosphere, sorry, we'll call that stratosphere jump from this place actually. You can see in our atmosphere, we don't just have one layer, we have a lot of layers. We have the bottom layer is troposphere, the second layer from the bottom is stratosphere, and then mesosphere and thermosphere and exosphere. Okay, so different spheres have different characteristics. We are going to learn in this lecture, in this chapter. So that is a very important thing you want to know in this lecture. Okay, and there's the game. Let's play with the game in our live meeting. Okay, so this is the study guide. Those are the 5 key topics we are going to explore and learn. So let's get started from the very first one, composition of the atmosphere. Okay, so keywords. The atmosphere contains a lot of gases, right? Well, not just gases, we also have particulates. Here, the solid part. Let's go to that page, air pollution. Here, our atmosphere doesn't just have gas. It also have gas or particulates, but not all the gas or particulates are air pollution. But I just want to let you know, we have solid and gas, okay? All right, speaking of gas, we have 2 types of gases, permanent gas and variable gas. So what is permanent? Well, their composition, the percentage, doesn't change that much from time to time, from place to place. So for example, the most abundant top 3 gases in our atmosphere is nitrogen, the first one. You can see the percentage by volume is about 78%. And the second one is oxygen. Oxygen is about 21%. Okay, and argon is a lazy gas. Well, that composition is about 0.93%. And you can see if you add them up, those 3 gases almost take 99% volume of our entire atmosphere, right? So they're abundant. Their percentage doesn't change that much, so we call them permanent gas. Okay, this teeny tiny slide, actually, that is we call the other type of gas. We call that variable gas or trace gas because the amount, the percentage is really small, so we call that trace gas. Okay, so what are they? Well, you're familiar with them. Carbon dioxide, water vapor. Make here note, water vapor is the gas phase of water. It's not our liquid water. Okay, it's the water vapor. And then ozone layer. Okay, and methane, and many others. Okay, so they're very small amount. They have very small amount, the percentage, but they change a lot from time to time, from place to place. So, for example, water vapor. Okay, well, you don't have to travel very far. Just in LA, in Santa Monica, the beach, you feel very moist. But if you go to San Fernando Valley, you feel the air is relatively drier, right? So that is different composition of water vapor in our atmosphere. Think about a place close to our freeways. You probably have a lot of carbon dioxide in your air, and close to maybe in our Santa Monica Mountains in the forest, you have less, right? So you can see those variable gas, they change a lot, okay? And particulates. Oh, here we go. Particulates. Those particulates is not gas. They are suspended or falling liquid or solid in our atmosphere. Okay, it's non-gaseous composition components in our atmosphere. Okay, so 3 key things right here. Remember, make sure you understand the difference between permanent gas and variable gas, and the top 3 permanent gas, and a few examples of your variable gas. Those gases in our atmosphere is not just to stay there forever. They're in a dynamic mode. They are very dynamic linking, we call that a matter, right? Through the matter of the flow of the gases, the matter, they link all the spheres together, the 4 spheres in our atmosphere. They're in our Earth system. They're atmosphere, hydrosphere, lithosphere, and biosphere, right? So you can see here, I give you this example about our carbon cycle. You can see starting from the sunlight, photosynthesis, right? And our tree, green leaves, they are going to fix carbon dioxide as a fuel, right? To make photosynthesis happen, okay? And then to make their leaves, those nutrients, sugar, right? Okay, and then when those leaves, they fall and they decay, they become organic carbon, right? Okay, and that animals also, when they dead, when they die, they become organic carbon, and those carbon actually into our lithosphere already, right, in the soil, and become fossils and fossil fuels, the rocks, right? And then people extract it from our lithosphere, right? And then we burn it to fuel our cars, auto and factory emissions, and emit the carbon dioxide back to our atmosphere, right? And plants and animals also help it, but it's not as the same amount as our auto and factory emissions, right? So you can see here, every spheres, they're linked by this matter flow, the flow of our carbon dioxide, right? Okay, so that is why when we study geography, we constantly need to apply this systematic thinking, in our case study. Why we have global warming, why we have more and more carbon dioxide in our atmosphere. We disturb this natural cycle, right? And they trigger a lot of issues like global warming and glacier melting, right? Many falling phenomena. Okay, so I want you to check out this link to read more about carbon cycle and other biogeochemical cycles like nitrogen cycle, water cycle. Okay, so and in our live meeting, we are going to explore this video together. Okay. All right. So another topic of this chapter is the weight of air and the air pressure. Okay, so how heavy the air is and why we have this layer of gas attached to our Earth's surface, right? So ultimately, that is gravity. Gravity keeps all the air molecules in the atmosphere and ocean into the planet, okay? And give them the weight. The total weight of our atmosphere is this million quadrillion metric tons. That is a huge number, right? So the weight and the movement of the air molecules, you can see it's very heavy, right? And the movement of the air molecules also create the air pressure. Like they can push onto you, right? They can give you this pressure. They also move even we cannot see. Even we cannot see them, but they constantly moving, they strike on our surface, give you this pressure. Okay, so two reasons for air pressure. Number one is weight. Number two is movement. Okay, so this is a very cool experiment to check out how air pressure, to prove people air pressure exists even we don't feel it. Okay, in our lab meeting, let's explore that. Explore it. But it's a simple one you can play in your kitchen. You have this cup, you fill that with water, 100%. Okay, and then you put like a cardboard on top of the glass, and then you turn that upside down, and you will see this cardboard won't fall off. Okay, because the pressure push onto it. Okay, try it. Okay, so then we need to measure air pressure, right? Okay, how to measure that? This is a very, very first instrument to measure it. We call that barometer. So that is why here when we measure air pressure, we call that, we use the unit bars, okay, bar, or many other units, but bar is one of them. Okay, so you can see how it works. You basically have this dish. You have this dish, and you fill that with mercury. Okay, and then you place this vacuum glass tube into this dish of mercury, and you can see here nothing in it initially, but you can see the air pressure push it down and squeeze those mercury into this vacuum tube. Okay, and the height of this mercury, okay, in the tube, and is how high our atmosphere can support this the weight of this height of mercury, right? So at sea level, this height is about 760 millimeter. So we call that 760 millimeter mercury is the standard atmosphere pressure measured at the sea level, okay, at the normal 15 degrees Celsius. Okay, so that is how you measure it, and you can see you have many unit, like your distance, right? You have many unit to measure air pressure. We commonly use millimeter mercury or Pascal or millibar. See here, barometer, millibar. Okay, so here those numbers are constant. They're called standard atmosphere pressure. So 1 atmosphere, okay, pressure, standard pressure equals to 760 millimeter mercury, 1013.25 hectopascal is another unit, and 10, the same number of millibar, same thing, and PSI is pounds per square inches. Means at the sea level, every square inch, you have this many pounds. That's a lot, right? But you can see I constantly emphasize this the sea level pressure, because as long as you go up, air pressure always decrease. Okay, air pressure always decrease because gravity. Gravity keep most air molecules close to Earth's surface. You have a lot of air molecules. You have a lot of air molecules strike onto you, right? And also you have the very largest amount at the sea level. So that is the highest number. But when you go up, you can see at the peak of the mountain Everest, it's about 33% of that at the sea level, because you have less air molecules on top of you and you have less air molecules striking onto you, right? So that is air pressure. How to measure it, those constant number at the sea level, and how that change with height, okay? All right, so the layers in atmosphere. Okay, like I mentioned earlier, we have 5 layers, but the very top layer, exosphere, basically is the universe. Okay, so we are going to focus on the 4 spheres listed here. From bottom, troposphere. So see here, troposphere, altitude 0 to 12. Okay, and important features. This picture is from your book. In your book, please make sure to read carefully about this part. Okay, so important features, the layer of atmosphere in contact with the surface, okay, where people live. All weather occur here. So we see snow, we see hurricane, we see winter storm, we see wind, right? We see a lot of weather events. They all happen in our troposphere. Why? Because here, strong convective mixing. What's that? Let's go to the next page. Okay, so because here, this is the important thing. This is the reason. Temperature decreases as elevation increases in troposphere. Means, let me go back here. Okay, here this red line represents temperature. Okay, so you can see when you go up, temperature decreases in troposphere. Means you have warm bottom, you have cold top. Cold air is denser, it's heavier, so they're going to fall. But warm air, they are light. They are going to rise. So we call it convective mixing. Okay, so when you have the warm air rise up, you are going to carry a lot of moisture up, right? And then when they contact with cold air, they are going to condense. Condensation will happen. That's why we have cloud, right? Okay, so that is why. Okay, it's just because it's temperature profile. Okay, so here's the thing. You may wondering how fast the temperature decrease. Here we go. This is the rate. We call that environmental lapse rate. Global average, people, global average is about 1 kilometer. If you go up by 1 kilometer, you need to decrease your temperature 6.5 degrees Celsius. Okay, if you use feet, that is 1,000 feet, 3.5 degrees in troposphere when you go up. Okay, and it trapped all the water. Okay, 80%, not all, 80% of the atmosphere mass and water. Okay, almost all the water actually. Strong convective mixing and highest water content, right? Okay, and highest concentration of aerosols. Those are the solid and liquid particles in our atmosphere. Okay, it's just because this convection, this convective mixing is just in troposphere, because as you can see in our stratosphere, temperature have different changing trend. When you go up, temperature increases. So in stratosphere, it's very stable actually. It's very stable. We call that temperature inversion. Means at the bottom it's hot, and bottom is cold, at the top is hot. So you can see bottom is cold, it's very stable, right? So very little mixing over there. Okay, only horizontal flow. That is why most airplanes, they want to fly at this level, because you don't have up and downs. The airflow is safer. Okay, and then continue to our continue on from our stratosphere, we will pass the stratopause into mesosphere. Mesosphere, you have similar temperature trend as troposphere. Okay, so you will have mixing, but you won't have weather because almost all the water vapor is constrained over here. Okay, so no water vapor, very little, very little. I won't say no, very little water vapor in our mesosphere. Okay, most meteors actually burn up in here. Okay, and that is the coldest region when you go up here in our atmosphere. Okay, so I forgot one more thing in our stratosphere, ozone. You have highest ozone concentration in stratosphere. That is our ozone layer that protect us from UVs from our sun. Okay, and then moving on from our mesosphere to the thermosphere. So you can see this is hottest place in our atmosphere, okay, because they actually absorb a lot of solar energy right here. But you know, here the temperature is hot, but if you go there, you won't feel it because you have a very little air molecules that can transfer their energy to you to feel the heat. Okay, so but many spacecraft craft they orbit over there. Okay, so make sure you read this part very carefully in your book to learn the four spheres and their characteristics. Okay, and here I just give you some basic facts to summarize the chapter. And this is the Hurricane Dorian in 2019. You will see the weather happening in our troposphere. Okay, let's explore that in our live meeting. Okay, so in addition to layers, okay, we also want to know the particles, the air pollution. Okay, so what is air pollution in the first place? Air pollution or air pollutant. Let's first learn what is air pollutant. It's a harmful concentration of gas or particles in our atmosphere. So basically it's bad for our health. Okay, pollution originates from two sources, natural and people. Okay, so we call that natural and anthropogenic sources. Okay, so for example, wildfire could be natural, right? And most anthropogenic air pollutants coming from burning by fossil fuels. Okay, when we measure air pollutant, we want to use PM10 or PM 2.5. What's the difference? That basically is that the solid or liquid particles, the size, okay? 2.5 measure everything greater than 2.5 mu amp micrometer. Okay, and PM10 measure everything greater than 10 micrometer. Okay, so it's if you compare the same place at the same place, you compare two numbers. PM10 actually is less than PM 2.5. Okay, and the air quality index is a commonly used index to indicate the air pollution in one area. Okay, so in your essay, you're going to use those index and PM 2.5 to explore the air pollution in your neighborhood. All right, speaking of air pollutants, you have two types. You have primary, that is enter the air or water directly from the source. Okay, but you also have secondary, which is more harmful, forms in the air or water through chemical reactions among primary pollutants. Okay, so you recook it. Okay, so for example, ground level ozone. Okay, ground level ozone. Ozone is protecting us in stratosphere, but at the ground, it's an air pollutant. Okay, and here you can see if you drive in LA in the afternoon, right, you constantly can see a layer of orange thing sustaining in our atmosphere, in our troposphere. What's that? That is your secondary pollutants. The primary coming from our car, cooked by our sun. LA is sunny, right? Cooked by our sun and make those more toxic gases in our atmosphere. You may heard smog, right? So that is all secondary pollutant. Okay. In 1970s, go back here. In 1970s, air pollutants, especially smog, actually is pretty dangerous, pretty bad in LA. But we passed that Clean Air Act, right? We concentrate our energy and money to clean our air. And you can see now, LA is much better than 1970s. Okay, so in our live meeting, I'm going to share with you a video to check out the smog in 1970s in LA. All right, so temperature inversion and the smog. Okay, why it is so dangerous in a place like LA? Sometimes we're going to have this temperature inversion. What's that? Well, at the bottom, you have cold air. At the top, you have warm air. So this layer is very stable. You can see cold is heavy, right? Light air is on the top. So you don't have that convective mixing. Okay, we call that inversion layer. And this inversion layer is just like a lid on top of your glass, right? Okay, so you can see if you have a big city down here, all the air pollutants, they're going to be trapped under this inversion layer, right? So that causes our smog more serious, okay? Well, when it will happen? Well, in the winter. So in the winter over the long night, right? So our air at the bottom is cold, but on the top is still warm because it takes time to transfer the ground heat energy to the top of a troposphere, right? So then in the early winter morning, this temperature inversion is very common, okay? So it's not a good idea to run in the very early morning in winter, okay? This video explore more about this, okay? All right, so very last slide is about ozone depletion. Okay, so here, especially above our Antarctica, we have this ozone hole. Okay, so what's happening over there? CFCs, man-made chemicals. Okay, used in our fridge, for example. Okay, so that is CFC and our sunlight, the UV together break our ozone in stratosphere. Okay, so you can see the CFCs, okay, they're not stable in our atmosphere. They're going to release this single chlorine atom. And then this chlorine atom will break our ozone, O3, okay, into two parts, common oxygen, O2, and they're going to grab the oxygen atom over here to form something like this, chlorine monoxide, okay? And then this one, this ClO is not stable. This one will break apart, okay? Later, you release chlorine and oxygen atom. And then you can see this chlorine atom can be reused again to break more ozone, right? So that is why in 1980s, this problem is very, very serious, okay? Because people at that time, they don't know how to replace this, CFCs in our fridge with another material to reduce the CFC in our atmosphere. Make sure you explore how CFC and UV together work together to break our ozone layer. Okay. All right. So this is the very last slide. I'm going to stop here and let me summarize in this chapter. We are going to learn the composition, weight of the air pressure, how that changes, how you measure it, okay, and the layers in atmosphere and the characteristics, okay, and air pollutants and ozone depletion, okay. Make sure you read your chapter and the videos I posted on the study guide, okay. I will see you in lecture. Bye for now.